Hello, everybody, and welcome to today's webinar. My name is Elena Sturman. I am the President and CEO of the Glaucoma Foundation. Since our founding in 1984, the Glaucoma Foundation has worked to encourage and support basic and applied research in glaucoma with the goal of preserving and restoring vision. Our board of directors and scientific and medical advisory boards are dedicated to identifying the most promising avenues for research. Our annual think tank brings together scientists from all over the world and from different disciplines to work on the problem of glaucoma. I'm very excited to bring you today's webinar with Dr. Calvin Roberts on THEA, Transplantation of Human Eye Allografts. THEA is a national program designed to bring together the expertise of vision scientists from multiple universities and laboratories. Their goal is to restore vision in the blind by transplanting a donor eye. Dr. Roberts is a program manager in the new Federal Health Agency, Advanced Research Project Agency for Health, or ARPA-H. He is also a president and chief executive officer of Lighthouse Guild, and a clinical professor of ophthalmology at Weill Cornell Medical College. Dr. Roberts is credited with developing surgical therapies, over-the-counter products for vision care, prescription ocular therapeutics, and innovative treatment regimens. Dr. Roberts hosts the podcast series on tech and vision, where innovators discuss how rapidly evolving assistive technology creates equity among those who are visually impaired. As always, there will be a question and answer session at the end of the presentation. You can pose a question by using a chat or Q&A button, and we will do our best to answer as many questions as we can. Now, ladies and gentlemen, it is my great pleasure to welcome Dr. Calvin Roberts. Let's begin.
All right. Elena, thank you very much. Thank you very much. All right, let me share my screen. So this first slide that you're seeing here is a piece of art that's in the Renwick Gallery in Washington, D.C. And for those who can't see it, it says, "This present moment used to be the unimaginable future." What does that mean? That means that what is commonplace today, not that long ago, was unimaginable. And so the theme for today is just that, to be open-minded about what might be in the future that is unimaginable today. So examples. So examples of everyday technology that were once the unimaginable future include the internet, GPS, autonomous driving cars, the graphic user interface we all use on our computers, and the use of mRNA technology to make vaccines. So none of these technologies were a result of a panel of senior scientists sitting around building consensus on research priorities. No. Rather, they were the brainchild of individual scientists with big, bold ideas who were fortunate enough to be at DARPA, the Defense Department's Advanced Research Project Agency, in a setting that allowed them to pursue their wild ideas with freedom. Now, in healthcare, we don't often see this level of technological innovation. In my career in ophthalmology, Charlie Kellman invented phacoemulsification 50 years ago. And other than the femtosecond laser and OCT, most technology advances have been iterative. So a couple of years ago, some futuristic congressional leaders decided that if the United States was going to maintain its dominance in healthcare innovation, we needed a DARPA equivalent for health. that would solely work on big, bold, high-risk, high-reward, so-called moonshots in healthcare innovation. And that concept became ARPA-H. So ARPA-H is the Advanced Research Project Agency for Health. And our mission here is to accelerate better health outcomes for everyone. And so equity is a key part of what we're doing. It's not enough to come up with great innovation. We must make sure that that innovation is available to everyone. So ARPA-H is different than any funding agency that I've ever had anything to do with. First of all, how does it fit in the government? It's a division of Health and Human Services, like NIH is, but it's separate from NIH. So it's not part of NIH. It's its own agency. Excuse me, for example, it has no internal research labs. And so this is just, it's a funding agency that we don't do the work ourselves. We are agnostic to disease. So we treat all comers. We began with $2.5 billion of appropriation. And again, our budget is independent from that from NIH. What we do is we fund outcome-based contracts, not grants. And so I like to always stop and make the difference between what we do at ARPA-H and what they do at NIH. At NIH, what they do is they fund research. And so what's research? Research is the desire to get new knowledge and to learn more. Start with a problem and study it and learn more. But what we do at ARPA-H is very different. We're more the D in R&D than the R. And so what we're looking to do is develop new concepts and new therapies using the research that's already there. The way it works is what we call the bottoms-up problem-centric approach, which means that rather than priorities being set from the top as to what areas we're going to look at, it really starts with the program managers. And the program manager is the one who come up with the ideas of the programs that we're going to do. Interestingly, program managers, all of us at ARPA-H, are term limited, which means that we're hired for 3 years. The agency has at its option the opportunity to rehire us for another 3 years, but certainly by 6 years, everybody's out and a whole new crew comes in. And so the idea is to always bring in new people with new ideas and new sense of urgency so that we get things done. So ARPA-H starts with the program managers. And so the program managers are responsible for the full program lifecycle, for creating a program and then bringing it to fruition. At ARPA-H, we're not looking for evolutionary or iterative changes. We want radical changes, things that are big and bold and really, really hard. And the program managers, I have to tell you, my job is the best job around because I'm empowered to create the programs, develop them, decide how it's going to be implemented, and follow it through. And again, don't have a lot of time here, so eager to make things happen. So what happens? So the program manager identifies the problem. And one of the things I love to say, fall in love with the problem, not with the solution. All right, because you want to be relatively agnostic to the solution, because if you fall in love with a solution and it doesn't work, you may want to hang on to that as opposed to, you got to be willing to try the next solution. So the program manager identifies the problem. Again, challenge should not be easily solvable. And so it has to be something that's really, really hard. Then the program manager launches the program and chooses a group of performers who are then there to execute on this program. So there are very, very well-defined metrics of what you have to do and timelines. And everybody has to hit their metrics and hit their timelines. And inherent to this program is that we'll start out with several performers, and over time, we'll drop some out. The government has a great euphemism for this. The government says they are down select, that we down select. So we may start out in this, as in this diagram, with 3 performers and only at the end land up with 1. Within ARPA-H, there are 4 areas that we're concentrated on. I'm in the group called Health Science Futures. And so what that means is that these are the radical new medical discoveries, the stuff that's really, really out of the box. But there's another group within Scalable Solutions. And what they're addressing is, how do we get the same quality of healthcare that you say might be at a major medical center? How do we get that same quality of healthcare available to everyone across the country and internationally? Which means, how do we manufacture? How do we collect data? How do we share data? How do we scale innovation so that it's available to everyone in an equitable way? Proactive health means, how do we keep people healthy? And that means not just on an individual basis of how do we keep individuals healthy, but how do we keep our society healthy? How do we promote healthy behaviors? And how do we make the workplace healthy? How do we keep the American people from being susceptible to viruses and bacteria and so many things? How do we keep people healthy? And the final group is what we call resilient systems. And what this means is, how do we keep our healthcare up and running when there are crises, whether it's the pandemic, whether it's weather, whether it's something else that happens? How do we make sure that our healthcare system continues to function? So ARPA-H has really just been going for a little over a year. And what you see on the top of this chart are the programs that have been launched since May of 2023, just in the last year. What's on the top line are what we call our programs. What you have below the line is what we call our projects. Now, what's the difference? Programs come from program managers. So someone like myself who develops a program, puts it together, and launches it. However, there's also an opportunity for anyone to come and propose an idea. And if your idea is accepted, then it becomes below the line as one of our projects. And so there's a lot of projects there that have been proposed by people outside of ARPA-H who have great ideas and who brought those ideas to us. Let me give you a couple of examples of what I think are really, really interesting programs. So here's this first one. We call it Nitro. You know, in my age group, so many people I know are getting new artificial joints. They're getting a hip replacement. They're getting a knee replacement. They're getting a shoulder replacement. Well, what if no one ever needed to get an artificial hip or shoulder or knee because your joints never wore out in the first place? How about if we could just eradicate osteoarthritis so it never happened, so that everybody's joints always stayed healthy? Wouldn't that be great? Here's another one. This one's called precision surgical interventions. So think about what happens when someone goes for cancer surgery. What the surgeon wants to do is the surgeon wants to remove the tumor and make sure to get all the tumor out, but take out as little of the normal tissue as possible. And we all know that some of the major complications that are associated with cancer surgery, besides the cancer, is accidentally cutting nerves, cutting major blood vessels. Those are some of the big complications that happen. So what this program wants to do is give the surgeon visualization so that when the surgeon goes into cancer surgery, knows exactly where the margins are. So you can cut exactly all the tumor out without cutting out the normal tissue, and lets you see exactly where the nerves are, and lets you see exactly where the blood vessels are, so you work around them so you don't cut anything that you shouldn't cut. Wouldn't that be really great? Here's another one that I love. We call it Apex. You know, how is it that we create vaccines in the country today? We do vaccines for an individual virus at an individual point in time. Look at how many times we needed to get boosters on our COVID because the virus mutated. We needed to get a booster shot. But what if we didn't do vaccines to individual viruses, but we did them to whole families of viruses, what we call genuses of virus, so that one vaccine was capable of blocking infections from 10 viruses or 15 viruses or 20 viruses. That if you got 2 vaccines or 3 vaccines, you were covered for 50, 60 viruses. You know, currently there are 275 viruses that infect humans, and we have vaccines for 17. 17 out of 275. Well, how about if we could do vaccines for whole families of viruses? We could eliminate 30, 40, 50, 60 of those viruses from infecting people. Just think what improvement in health that would be able to accomplish. Here's another one. What Ryan Spindler, the program manager, what he wants to do is to 3D print human organs. So let's say that you needed a new heart. Well, what you would do is draw a tube of blood. From that blood, you would grow stem cells and to develop the individual types of cells that you need in a heart. There are muscle cells, there are nerve cells, there are blood vessel type of cells, there are all kinds of different cells that are in, say, a heart. And then you use a 3D printer and you printed out a new heart. And now you had a new heart that was made up of your DNA, of your cells, and you didn't need a donor, and you didn't have to worry about rejection because it was all your tissue. And you could do that for hearts and do it for livers and do it for kidneys. Wouldn't that be exciting? And here's another one. What this program is doing is looking at the lymphatic system. You know, the lymphatic system is probably one of the major organs for which medicine knows the least. We've all heard of lymph nodes, and which are just areas of collection of lymph. But your lymph system is like your blood vessels. It goes throughout your body. But really hard, at this point, impossible to visualize. So what if you could visualize your whole lymph system? Well, then you could make diagnoses and do treatments that we could never imagine. So that's another example. So those are a couple of examples of what some of the other program managers are working on. Now let me talk to you about what I'm working on. As Elena said, my program is called THEA, which is an acronym for Transplantation of Human Eye Allografts, which means what we want to do is we want to take eyes from people who donated them, put them into people who are totally blind, and restore their vision. And I put this slide up, which is always a reminder that the eye and the optic nerve are nothing more than the anterior extension of the brain, which means that if we're transplanting an eye, what we're doing is transplanting a part of the central nervous system. No one's ever been able to successfully transplant a piece of the brain. And so if we can transplant eyes, it just opens up so many other potential possibilities. So we transplant hearts, we transplant lungs, we transplant livers, we transplant kidneys, we transplant skin, we transfuse blood. So why don't we transplant eyes? Because if we were to transplant an eye, we would have to transplant and reconnect all the nerves associated with the eye. Most importantly, the optic nerve, which carries the message to the brain. But there are a lot of other nerves that are involved with the eye. There are the nerves that connect to the front of the eye and give sensation to your cornea. There are the nerves that move your pupil and cause your pupil to get big and get small, type of thing. There are the nerves that innervate all the muscles. So there's a big job to reattach the nerves. And the blood vessels are really small. You have to figure out how you're going to reconnect all these blood vessels and all these muscles. It's going to be a hard thing to do. But if we could, we might be able to restore people's vision. So when I think about the common eye diseases, often we divide them into those that affect the front of the eye and those that affect the back of the eye. And while for the back of the eyes, the three leading causes of blindness in this country are, of course, glaucoma, diabetic retinopathy, and macular degeneration. For each of those, we have better and better therapies to try to slow down the progression of the disease. But for none of the conditions of the back of the eye do we have any therapy to actually restore vision after you've lost it. For conditions of the front of the eye, it's very different. If someone has a cataract and loses vision from cataract, we can do cataract surgery and restore their vision. If someone has a problem with their cornea, the front of the eye, you can do a cornea transplant and you can restore their vision. So what we want to do is bring restorative medicine to back of the eye conditions that we already have with the front of the eye. So let's use the model of how we restore vision for people with cornea disease and see how we use that to help us with back of the eye. So what do we know? We know that over 70,000 people donate their eyes every year for transplantation, and there are about 40,000 surgeries that are done every year. How does it work? Well, when someone dies and they donate their eyes, then hours later, someone goes and harvests the eyes, brings the eyes to the eye bank where they can be stored for a week or even more, after which they're brought to the hospital where the surgery is going to take place. Usually it's an ophthalmologist or cornea specialist who does the surgery. We're very fortunate that corneas are what we call immunoprivileged, which means that corneas don't often reject. Happens occasionally, but doesn't happen often. And fortunately, the vision is restored in weeks to months. So let's compare that to now what would we have to do if we were going to transplant whole eyes? Well, first of all, what we have to do is not get them from people who have died, but we have to get them from what are called organ donors. Those are people who are donating their hearts, their livers, their kidneys. These are people whose hearts are beating, but they are what's called brain dead, and consequently, before they die, they consent to be what are called organ donors. Now, what do we know? We know that when you take an eye out, it only survives for a matter of minutes. So what you have to be able to do is to harvest the eye from the donor and come up with some kind of system that you're going to immediately preserve that eye and keep it viable. Now, we're going to bring it to the site of the surgery, and we got to figure out, first and foremost, how are we going to reattach the optic nerve? How are we going to get that optic nerve to connect back to the brain of the recipient and restore vision? And the surgery is much more complicated. This is big surgery. We're requiring neurosurgeons and plastic surgeons and ENTs. So it's a whole team of people doing this. When we're transplanting whole eyes now, immunology is important. These eyes can reject. We got to figure out, how are we going to keep these eyes from rejecting? And of course, the restoration of vision is going to be slow. So how are we going to know how the people are doing, and how do we know that these eyes are actually healing? So we identified each of these as hurdles: the harvesting, the reattachment, and the surgery. And so the term that we use is, we call these technical areas, 1, 2, and 3. And so technical area number 1, as I said, how are we going to harvest these eyes and preserve them? Technical area number 2, how are we going to reattach the optic nerve and the other nerves such that they're capable of transmitting a signal that the brain can now interpret as vision? And number 3, how are we actually going to do this logistically? How are we going to do the surgery? How are we going to monitor these people? How are we going to treat them, prevent inflammation? How are we going to know how these people are doing? So I prepared this little video here just to show you a couple of ideas of what people have postulated as how you could reattach an optic nerve. And so what we know that the optic nerve's job is to transmit light back to the eye. So how could you do this? So one option is what we call a nerve wrap. So you would put something around the two ends that would bring the two ends together and get the eye to refunction. Another way is what's called electrical stimulation. This is what happens, how nerves are formed in the first place. Give electricity, make it grow. Third is the use of stem cells. So maybe stem cells could act as a bridge to connect the two ends of the nerve, the donor and recipient, in order to make it function. So where are we on this? Well, we announced this program beginning of January. In February, we got our proposers day, where people who are interested in being part of this could get together. We asked for expressions of interest in the form of abstract the 1st of March. We got back to those who had proposed in a couple of weeks, and asked those who were interested to get full proposals to submit them, which they did a couple of weeks ago. We're now in the final stages now of deciding who those proposers are going to be. And we want to get everybody contracted and up and running just in the next couple of months and get this program going. So, as I said before, and I started this by saying, at ARPA-H, it's not enough just to do the technology. We got to make it available. We got to make it available for everyone. And so in the short term, what we're doing is developing the technology, developing the necessary drugs and devices that we need to do, and how we're going to do the surgery. But we also want to engage the community and get people to understand what we're doing, get people aware, embrace and be embraced by the whole ecosystem of organ procurements, and make this the way it is to get a heart or get a liver or to get a kidney should be how it is to get the eyes, and prioritize education among patients and among doctors. One final thing I want to talk about is another program within ARPA-H, which is what we call the Sprint for Women's Health. I think that everyone understands that women's health has not received the priority that it should. And so at ARPA-H, we are committing $100 million for just new ideas as to how we can advance the healthcare for women, both technically and how we're going to make women healthier, how we're going to make sure that women get the kind of care that they should. And so this is a program that is currently underway. This is a really quick program. This one started just with requests in February, had Proposers Day in March. A very, very quick way of deciding, and these awards will go out just in the next couple of months. So I leave you with the way I started, which is to say that be open-minded for things that might be able to occur. And if we are, and if we're fortunate, and if some of the programs that I described today can work, wow, wouldn't that be a wonderful future? So thank you. Now I'm eager to hear questions that you may have, but to make it easier on everybody, I wrote down the questions that other people ask. So let me start by asking the questions that I often get asked. Maybe they're the same questions that you might have. So the first question people ask me, how much money are you spending? Government, unfortunately, doesn't release that number. But what they do allow me to say is that this program, once we're up and going, will be the second largest funder of eye research in the world, second only to National Eye Institute. Second question, what percentage of ARPA-H spending is for ophthalmology? Doesn't work that way. There isn't at ARPA-H a designation of certain amounts of money for each specialty. So it's not like NIH, where the National Eye Institute gets 5.1% of the NIH budget every year goes to the National Eye Institute. No. How it works at ARPA-H is you have a bunch of program managers like myself who come up with ideas. And the best ideas are the ones that get funded without respect to what the area is. Question number 3. Is this money that would otherwise go to the National Eye Institute? No. And that's what really, really is gratifying for me. This is all new money for eye research. So we're just expanding the pie for eye research. We're bringing in all this additional money into the whole ecosphere of vision research. And so I'm really, really excited about the fact that ARPA-H is just going to allow new research to happen over and above that which was already possible. Number 4. Didn't I already read about an eye being transplanted as part of a hemifacial transplant? Yes, you did. So just about a year ago at NYU, as part of with a whole face being transplanted, they transplanted an eye as well. That's a very important event, because while it wasn't meant to give the person vision, and it didn't give the person any vision, what it did show is that you could keep an eye alive. And so that's a very important landmark, and one that we're going to build on now, because our goal is to allow people to be able to see after a transplanted eye. Number 5, if you're also already spending all this money, why not spend it on developing a bionic eye? You would not be dependent on donations. You would not have to worry about rejection. Correct. Yes. Wouldn't that be a great goal, to have an electric eye, a bionic eye, something that you didn't have to need an eye for transplantation? Well, I'm sure we're going to get there someday. But I use the example of hearts. So 60 years ago, in 1964, NIH came up with a task force with the goal of building a mechanical heart to get an artificial heart. That was 60 years ago. And the first mechanical heart was implanted in 1982. Maybe some of you remember the Jarvik II heart. Well, it's now 42 years after the Jarvik II, and there's not a single person in the world walking around with a mechanical heart. That heart transplants are still the gold standard for treatment of people with end-stage heart disease. So, will we have bionic eyes one day? Yes. But I think that for now, if we can transplant eyes, we'll be able to restore vision, and we'll learn so much in the process that actually will make it that much easier to develop bionic eyes in the future. And the final question, and this is my favorite, people ask me, do you really think this is going to work? And my answer is yes. The science that is out there, that has been developed just in the last 10, 12 years is amazing. Or, like this art says, unimaginable. And so I think that we have a really, really good shot at making this work. Okay, so those were the questions I had in advance. Elena, you got some others?
So fantastic presentation, Dr. Roberts. If you don't mind, stop sharing your screen so
Sure.
The audience can see you on the screen. Perfect. So thank you for letting us speak into the future. And also thank you for knowing your audience so well, because you've answered most of the questions that were in the chat. There are some that you haven't still, and I'm going to pose them to you, but kudos to really knowing your audience. So question number one, is ARPA-H open to international participation or only to US participants?
Yeah, so that's a good question. So the answer is yes. We are open to international participants. And so that if an international participant has some unique know-how, knowledge, ability to help us with our program, yes, we absolutely are open to it.
Excellent. Next question. Are people outside of the US able to benefit from these innovations, and how much are they looking at spending?
Well, so, when ARPA-H says better healthcare for all, we really do mean all. And a lot of the programs that we're working on at ARPA-H are really actually looking primarily internationally, and looking at areas where healthcare is underserved, and really asking the question, how do we get high quality healthcare in areas of the world that don't have it? How can we improve healthcare for all?
Thank you. Thank you. And now is the question that I'm sure you're getting all the time. When do you expect to begin? And
Well,
are you now looking
yeah.
for volunteers?
Well, yeah. So we're working at record speed to get this program up and running. We're going to have it up and running in the next couple of months, get everybody funded and get everybody working. The way the ARPA-H works is you have to design your program so that you complete it within 4 to 5 years. And so it is certainly our goal to be able to do these eye transplants within the next 5 years.
That's really amazing. That's really amazing. Next question. Would the brain be able to translate images from a transplanted eye?
Yeah, good question. That's a good question. So there's a term that we use that we call plasticity, and brain plasticity, which means the ability of the eye to work differently than it was originally designed to work. And so one of the questions is a great question is, will the message coming to the brain from a foreign eye, from a new eye, be interpretable by the brain? Now, there's some very, very good news here. And the good news is that every human's eyes transmits the same signal. So the message that your eyes send to your brain is the same message that my eyes send to my brain. They speak the same language. They work the same way. So that's important and very good news to know that all our eyes work the same. And so that the message will be the same as when received from a donor eye as received from the recipient's original eye. Now we just got to hook everything up so the message gets there.
Thank you very much. Thank you. And this is the last question. So the question is, how, when you're ready to transplant the whole eye, how will you select the participants? Who will be given a priority, and how will it be done?
So, so the first priority is going to be people who are totally blind. And so that's the first. And because, from the medical theory of at worst do no harm. So we want to take people who have zero vision and try to give them vision. And we don't want any situation in which we could hurt somebody's vision that they already have. So that's the first thing. Second is that equity is very important. That we want to make sure that the opportunities are there for everyone, and that there is a balance between people of gender, race. Make sure that the opportunities are available to everyone.
Thank you very much. Would you mind answering, because our audience is writing ferociously, and as I think that we've answered all the questions, there are 4 more. Would you be able to stay on maybe another 5-10 minutes to answer a few more questions?
Of course.
Thank you. So here's another question. What would be the side effects associated with the immunosuppressant drugs after the eye transplant?
Yeah, so I don't think this is any different than what happens when someone gets a new kidney or gets a new liver. And so I think that the drugs that we're going to use are very similar to the ones that are already out there in existence and have been tried. And so I think that whatever the potential side effects are, these are going to be with drugs that have a lot of experience, so that we'll be able to tell people well in advance, so they'll know what the potential risks of the medicines are.
Thank you very much. What about if someone is visually impaired from birth? If they got an eye transplant, would they see better or the same as they saw with the impaired eye, what they did with their whole life?
Yeah, I think that at least initially, I think that we're going to have to go with people who had vision and because with people who didn't have vision from birth, the wiring within the brain is not fully developed. And what we're doing here isn't going to rewire the brain. We're going to have to use the wiring that's already there.
Thank you very much. Okay, now this is the last question. Do you need HLA matching test before the surgery?
Yeah, I think that it's too soon to know exactly how we're going to match these eyes from a genetic point of view, whether HLA matching, whether it's blood type matching, whether we find other factors to decide which eye is suitable for which candidates. And I think that's stuff that we still need to work on. But remember, this is foreign tissue, and so that we're going to have to match it in some way to minimize the chances of inflammation and rejection, because eyes don't like inflammation, that's for sure. So we got to make sure that we have the least possible inflammation.
Thank you very much. So we've reached the end of our webinar. I would like to thank Dr. Roberts so much for letting us peek into the future, and hopefully in 5 years it will be a reality and blind people will be able to see. I would like to thank our audience for listening and for participating. This webinar will be available on our website and YouTube channel tomorrow if you would like to look at it again. And please stay in touch with us. And thank you so much again, and have a good evening, everybody. Bye-bye.